We would like to introduce you the application of Rutherford backscattering spectrometry and elastic recoil detection analysis methods on organic samples. RBS with complementary ERDA can be used for compositional thin film analysis, determination of the area concentrations, elemental depth profiling, and determination of the film density of the amorphous material. RBS and ERDA are a non-destructive ion beam technique. RBS is unique in that it allows quantification without the use of reference standards to ERDA, but it is limited by low sensitivity to light elements. Sensitivity to light elements can be partially improved by use of resonant cross-sections. During the RBS measurement, the samples are irradiated by light-energetic ions, then the elastically backscattered from nucleus inside the analyzed solid and subsequently detected at large angles. ERDA uses heavier ion than target atom to recoil low-mass target atoms and to measure their depth profiles. The ion projectile need only have a mass greater than the target atoms. Alpha particles are commonly used to obtain recoil spectrum for hydrogen and its isotopes. In our laboratory, we use RBS in Cornell geometry. The ion beam enters to the sample at zero angle and the backscattered particles are detected by a detector located 10 degrees below the beam. The scattering angle is typically 170 degrees. Energy of use ions during RBS is in order of MeV. The mass of the target atoms could be identified from the energy of the backscattered projectile. The backscattered particles are detected by the semiconductor detectors and thus we obtain the typical RBS spectrum. We use ERDA in IBM geometry, where incident beam, exit beam, and the surface normal are in the same plane. The ion beam enters to the sample at 75 angle, and the recoil particles are detected by a detector located 150 degrees below the beam. Before this detector is placed polymeric foil, which is the trap of the heavier ions. The scattering angle is typically 30 degrees. For ERDA measurement we use usually 2.5 MeV with helium ions, and from measurement we obtain the typical ERDA spectrum. Using the RBS and ERDA methods, we can analyze polymeric materials such as polyimide or polyethylene terephthalate. In this case, both polymers were implanted with low-energy gold ions with an ion fluence of 1/1016. Polymers were analyzed using 1.7 MeV helium ions incident on the sample at 0 degree and scattered at 170 degree. The result of the measurement is an energy spectrum describing the dependence of the number of helium ions incident on the detector as a function of their energy. For the RBS spectrum as characteristic edges, where each edge is characteristic of a given element. The information about the atomic concentration is given in table. Another example is the analysis of the polymer topaz. Single samples of this polymer were implanted with 1 MeV gold ions. From RBS analysis, it was found that oxygen exhibits non-monotonic evolution. Initially increasing at low fluences, then stabilizing or slightly decreasing at higher fluences, likely due to competing irradiation-induced oxidation from residual atmosphere and oxygen loss via bond scission and sputtering. Results show that increasing fluence systematically raises the carbon content while reducing hydrogen, reflecting progressive hydrogen depletion. Graphene oxide, which was prepared by Humer's method, was analyzed by RBS and ERDA to determine its atomic concentrations of elements. Graphene oxide was analyzed using 1.7 MeV He ions incident on the sample at 0 degrees and scattered at 170 degrees. From the measurements it is evident that the sample consists of 3 elements, carbon, oxygen, and nitrogen. A more detailed analysis indicates that carbon is 65%, oxygen is 19% and nitrogen is 3%. The presence of hydrogen was determined using the ERDA method as 14%. Graphene oxide was implanted with silver ions low energy, which were embedded into its structure. This graphene oxide was analyzed with 1.7 Me helium ions. The RBS method gives us information about depth profiles of implanted ions as well as information about the thickness of the individual layers present in the material. From spectrum on the left, we can determine the depth profile of the silver and the thickness of the implanted silver ion layer, which is approximately 40 nanometers. The spectrum on the right describes the silver depth profile extracted from the left spectrum. Experimentally determined depth profile can be compared with simulated profiles calculated by Monte Carlo program SRM. The above depth profile was taken for a graphene oxide sample that was implanted with 1.5 MeV copper ions. The ions were implanted to a depth of 1,500 nanometers. The depth profile shows that the measured simulation data exhibit a step. Setting the RBS parameters, especially the beam energy, is essential for obtaining detailed results. Each element has a different effective cross-section, which determines the signal intensity and is therefore crucial for interpreting the data and converting it into quantitative information about the sample's composition and structure. Comparing the two spectra shows that analysis at 2 MeV provides only basic information, such as elemental composition and approximate atomic concentrations. For more detailed insight, a higher energy is needed. In this case, using 3.07 MeV gives much better spectral resolution, allowing reliable depth profiling, for example, of oxygen. During the measurement we must count with several problems. First can be that the high-energy ion beams used in RBS or ERDA can lead to degradation of polymer chains, resulting in changes to their structure and properties. To prevent this degradation during measurement, it is important to use low ion energy, which helps reduce thermal damage to the polymer, or using low ion currents can further minimize the risk of damage. Another issue during polymer analysis is surface charging, which can distort results and make interpretation difficult. To obtain reliable data, this effect must be minimized. One option is to use an electron gun that emits electrons to neutralize the positive charge on the surface. Another method is to apply a thin conductive mask that covers most of the sample while leaving only the region of interest exposed. This prevents charging of the surrounding area and allows accurate analysis of the selected region. Thank you for your attention.